Hello, I'm Dr. Mariana Durcheva from Sami Shamoun College of Engineering, Israel, and as well as working at the Technical University of Sofia, Bulgaria. I want to share my thoughts about post-quantum security of tropical cryptography. What are the challenges and the perspectives? First of all, why post-quantum cryptography? As is well known, classical cryptography, such as RSA, the Diffie-Hellman key exchange, or elliptic cryptography, they are based on hard problems like integer factorization or discrete logarithm problems that could be solved by quantum computers due to Shor's algorithm. So we need for post-quantum cryptography. And the challenge is no longer to build cryptography that is hard for classical computers, but cryptography that remains secure in the quantum era. Why tropical cryptography? Tropical cryptography uses operations that are minimum or maximum. It is based on idempotent semirings, uses tropical matrices and other non-classical algebraic structures. Why considered for post-quantum cryptography? Since this type of cryptography is not directly group-based, often non-commutative, Shor's algorithm doesn't directly apply, and because of the rich nonlinear algebraic behavior of these structures. Two main tropical semirings that I'm using are min plus semiring and max plus semiring. In min plus semirings, the operations are very simple. Addition is minimum, multiplication is usual addition. In max plus semiring, the difference is that the addition is maximum. Tropical matrix algebra is based on tropical matrices. We can define tropical matrix addition and multiplication in usual manner. For instance, I'll show you a very simple example. If I want to compute a to the second power, what I need to do, 1 times 1 is 2, 3 times 2 is 5. So in min plus semiring, the result will be 2. In max plus semiring, of course, the result will be 5. The main protocol families are huge. The huge percent of protocols are tropical sticker type protocols. Unfortunately, all of them have been broken. Another group is semi-direct product constructions, tropical matrix power function protocols, tropical signature schemes, and recently have been proposed tropical knapsack constructions, and these are the underlying hard problems. So what about quantum perspective of tropical cryptography? As I said, in tropical cryptography, no direct Shor reduction. So the key question is, does not vulnerable to Shor imply security? Fortunately, the answer is no. I want to show you why this happens. My central thesis is that tropical cryptographic schemes fail not because quantum computers directly solve tropical problems, but because tropical instances collapse into tractable structured systems. And main reduction mechanisms include reduction to linear systems, reduction via periodicity, reduction via optimization, reduction via inequalities, reduction via polynomial representation. I'll go through all of them. Reduction to linear systems, what I mean. For example, if we have key exchange scheme and the user, for instance, Alice, has this matrix as her public key, where this matrix W is her is the known public matrix, and matrices X and Y are Alice's secret keys, but they are Alice's secret keys, but actually Alice's need to invent two secret colors, X alpha and X beta, since here you can see the way her secret keys are built. Matrices M and N in this scheme are actually publicly known. So if we substitute X and Y in Alice's public key, we get this expression. So from here, we could recover the secret parameters from this tropical linear system, where Z is X alpha plus Y beta. So initially, the problem was nonlinear, but actually we see that the problem is actually linear, and these types of attack are based on these mechanisms. Another reduction is via matrix power is based on the observation that matrix powers become periodic. You see the sequence of matrix powers, and after some k, the sequence becomes periodic with period p. So we get this equality. And this is very bad from inventors of such protocols, since a to the k plus p power becomes equal to a to the k times some metric c. As a consequence, the inventor of the protocol thinks about who suggest huge powers, and he or she thinks about huge key space, but due to this property, this property shrinks the key space. The large exponents become predictable. Binary search type attacks become possible. Another reduction is via optimization. What I mean is that many tropical expressions turn into shortest path problem, optimization problem, linear programming problem, graph problem, dynamic programming problem. So, for instance, if I want to solve this nonlinear tropical problem, I finally need to solve run shortest path problem, which is actually reduction. And instead of solve complicated nonlinear algebra problem, I just need to solve, the attacker need to solve a run shortest path problem. Another reduction is via inequalities. What I mean is that initially we have nonlinear tropical problem, but since for instance, in min plus semmering, we need to find the minimum. So this problem transforms into the inequalities of this type and taking the supremum over all I. So actually, the problem becomes linear. This is huge reduction. Another reduction is via polynomial representation. What I mean, many tropical protocols use as use as their secret keys tropical polynomials of this type. For instance, Alice published her public key in such way. Actually, this matrix A is publicly known. So, and the coefficients are actually Alice's secret keys, Z0, Z1, and so on. So, if we want to substitute instead of X our matrix A, this is the expansion. So what we have? We have on one side a sequence of known matrices, and on the one side a sequence of unknown coefficients. And the attacker need to find only these coefficients, which is actually huge reduction. So what we have is from we begin with worst case complexity, with the problem which is hard tropical problem, but due to these reductions, we have actually a problem which is linear and the protocol instances complexity are often easily solvable. So, what are the lessons learned? The lessons learned are that we have three pillars of post-quantum security. Quantum resistance, no reductions to Shor's algorithm or hidden subgroup problems, mathematical hardness, of course, mathematically hard problem, and of course, structural security. No linearization, no periodicity, no optimization-based reductions. What about future directions? I saw several possibilities to save tropical cryptography. Use hidden invariants, such as multivariate cryptography, Zugeni-based cryptography, hidden subgroup invariant approaches, use hybrid systems, classical plus public key cryptography protocols, or use not, for instance, tropical semirings, but supertropical semirings, since they introduce additional layer of information, so-called ghost layer, and it potentially create new source of complexity. And of course, avoid optimization reducibility, avoid shortest path problem, linear programming, approximation problem. As a conclusion, tropical algebra is extremely powerful, but since it transforms nonlinear problems into structured and solvable forms, but on the other side, this strength may conflict with tropical hardness. So The core issue is not the lack of hard problems, but the structural tractability of protocol-generated instances. So I have one open question. Can we construct tropical semi-ring-based cryptographic primitives that avoid all of these reduction mechanisms simultaneously? I will be happy for cooperation if you have ideas in this direction. And thank you very much for your attention. These are my main work emails. Thank you.